Okay, so we have just relook what we have covered so far, and in the just as far as the fundamentals of photochemistry is concerned, the as we there are as far as the photochemistry law is concerned, there are two main law. First law of photochemistry, and then the second law of photochemistry. First law is Grothus-Draper law, and it states that only the absorbed light brings about the phototransformation, whereas the reflected light does not take part in the phototransformation of any phototransformation. On the other hand, the second law is the Stark Einstein law, which says that one quantum of light activates one molecule. So these are the two main laws as far as photochemistry law is concerned. First one is the adsorption. How much light is absorbed by the molecule brings about the phototransformation, and then second is the only one quantum of light activates one phototransformation. Now after discussing so far regarding the fundamentals aspects, the absorption, the absorption of light, giving the molecule from ground state to excited state, and then it can be brought about two ways: direct and indirect excitation, or you call it as a direct and sensitized excitation. Energy transfer, which again two types: energy transfer for phototransformation and electron transfer reaction. Electron transfer is again two types: homogeneous photoinduced electron transfer, where which both donor acceptors are soluble, and the second is a heterogeneous photoinduced electron transfer, where one is a biphasic reaction. Only one phase is one component, that is whether it is a acceptor or donor is soluble, other is not soluble neither in organic solvent nor in aqueous solvents, and then reaction takes place in the surface chemistry. We also discuss about the quantum yield and so on and so forth. Now coming to the main aspects of photochemical reaction, that is the photochemistry of few selected organic system, and the molecule on absorption of light goes to an excited state. Molecule on absorption of light goes to an excited state, A star. Excited singlet state or excited triplet state, they are high energy species, short lived. They undergo different photophysical processes like internal converter, insert system crossing. These are the non-radiative process, and then radiative process are fluorescence and phosphorescence, or it can undergo different photochemical reaction, and this different photochemical reaction like cis trans isomerization, photocyclization, photo rearrangement, and so on, and photo addition, and so on and so forth. And these different types of photo reaction once again depends upon the type of chromophore. What is the chromophore present in the starting material? The chromophore present in the starting material decide what type of photochemistry. And so first we will just see photochemistry of one by one. We'll just discuss about alkene photochemistry. We have already discussed. Now we are just looking back, and slowly we will try to look one example of isomerization, one example of cyclization, and so on and so forth, and then we go for diene and so on and so forth. So say for example, when we have diene, alkene, and then so if it is a trans alkene, and we know that the trans alkene is more stable than the cis alkene, and then but it is possible to bring about this transformation under photolytic condition. This is a reversible reaction. More under photolytic condition, it undergoes molecule goes to an excited state, and these excited states are dipole diradically species, and then there is the double bond character which is restricts the rotation of the here the molecule. Now it is a double bond character is lost, and there is a possibility of free rotation, and the free rotation is possible, and molecule can go to a cis orientation, and then like this, and then when these two radicals combine together leads to the cis isomer. So the mechanism or steps involved is extremely simple, and then the most important aspect here is the reversible reaction. It is always there is an equilibrium between the trans and cis. So it is not possible to 100% conversion of trans to cis or cis to trans, but is always in equilibrium. And as we have seen in the previous classes, this reaction, cis trans isomerization, follow the non-adiabatic reaction, where the excited reactant switches over to the ground state energy profile, and then the rest of the reaction is proceeds on the ground state reaction, and hence it is possible to excited state reactant to come back to as we have seen here, like this. The R going to R star, and then R star moves here and then switches over. So it is possible to, and that's why this is this is always in equilibrium. So if we have a proper substituent, in cis orientation, say for example, we start with trans steel beam C6H5, H in the presence of light, and then we go to a trans form, goes to cis form, C6H5, H and H. Now if we write this in a just a full benzene ring, now if we prolong irradiation, and then is a cis, we have two phenyl groups in the cis form, and then if we carry out the irradiation, then there is one pi bond, another pi bond, and then so 2 4 6. This undergoes 6 pi electron cyclization. 6 pi electron cyclization to give a dihydrophenanthrene, and then we end up with a product like this. So this shifts here, this goes here, these two double bonds are remain as it is, and then we have a so this is dihydrophenanthrene. Dihydrophenanthrene is the photo product, and then of course it goes back, it is reversible again, so it reverts back to the cis orientation. So if we have a proper substituent like two phenyl groups, where is not necessary phenyl group, or what we need is for 6 pi electron cycles is 2 pi bonds, 1 pi bonds here, 1 pi, and then 1 pi bond of alkene. So 6 pi electron cyclization is possible to give you dihydrophenanthrene. Dihydrophenanthrene, and then of course is under air oxidation, it aromatizes to give you a few phenanthrene derivative. Of course, that is not a photoproduct. Photoproduct is this one. So we have if we have a proper substituent in the cis orientation, first is the cis trans isomerization, and then cis isomer under prolonged irradiation may undergo 6 pi electron cyclization to give the dihydrophenanthrene as one of the important photoproducts, because we are from open chain, we are ending up with a condensed aromatic ring, dihydroaromatic ring system. Now there are several several examples of this cis trans isomerization followed by cyclization is reported in the literature, which we have already seen few examples. The basic is this reaction, cis trans isomerization, loss of double bond to generate a 1,2 diradical which has a possibility of free rotation. Then the two phenyl groups come to the same side, and then recombination is a reversible reaction, and then two phenyl groups may further under fertility condition may lead to 6 pi electron cyclization to give dihydrophenanthrene. Now these as I have mentioned, if you have a proper substituent in the cis orientation, you have a two phenyl group may undergo these type of reaction. If we have a phenyl group, or we have also seen another substituent like thiophene. So one of the double bond of this thiophene or one double bond of phenyl group may also go in similar. If you have a thiophene, or we have a furan, or we have a what we call it as a the furan may also undergo a similar type of rearrangement. Now coming to the so proper substituent. Say for example, if we have a COC6H5 HCOC6H5. This is dibenzoyl 1,2 dibenzoyl 1,2 dibenzoyl alkene. This is a one benzoyl group, another benzoyl group COC6 ethylene. So under photolytic condition, of course, it is reversible, may also undergo cis trans isomerization across these double bonds, and when we end up with a COC6 is a trans, we call it as a E isomer, COC6H5 H may so now this is Z isomer. So now you have two benzoyl groups on the cis orientation. Of course, it is it is in equilibrium, and trans 1,2 dibenzoyl alkene under photolytic condition may lead to the cis trans isomerization across these double bond, giving rise to a less stable Z isomer. Now this Z isomer, two benzoyl groups under further photolysis, under further light on influence of light, two benzoyl group undergo a interesting photochemical reaction that is called and phenyl group migration. So if you write this in a proper way, then by so you can just represent this like this: H C double bond O C6H5, and then we write here C double bond O and then C6H5. Right. So now in the presence of light, one of the carbonyl, either this or this. So one of the carbonyl gets excited, and it can add to one of the phenyl group of the adjacent carbonyl, and then it can represent like this. So we can have a six member transition state. Right, we have yes, of course is going 6H5 and is moving to this place, and then this already there is a double bond, and there is a positive charge here and the negative charge here. Of course, it is a zootronic species. Benzoyl groups want to on excitation going to diradical, and then conversion of this diradical to dipolar species are well reported in the case of enone systems and so on and so forth, which we have already looked into. Now this is intermediate is formed by the attack of the excited carbonyl on the phenyl group of the other benzoyl group to form this type of medium, and then this once again moves like this. Now you can see there is a cleavage of this bond. this bond cleaves. When this bond cleaves, the phenyl group goes to other side. So you can see now O C6H5, C6H5, there is a double bond here, and there is a double bond here, and then there is a carbonyl here. This is a double bond, and then of course H here. Now this is the intermediate, is a ketene. Ketene intermediate is formed by the this is a very interesting rearrangement when we have a two benzoyl group on the cis orientation. So when two benzoyl groups are the cis orientation, on prolonged irradiation, on the influence of light, one of the carbonyl goes to an excited state and attacks on the phenyl group or other benzoyl group. It gets this intermediate. There is a dipolar species, dipolar intermediate, which opens up through the cleavage of this bond to give this ketene. And then this ketene is, we know that this ketene is unstable, and then this decomposes in the presence of water to give you carboxylic acid or an methanol or ester. If there is a alcoholic solvent, ROH, in the presence of alcoholic solvent, ROH, you get an ester. So this is an acid and this is an ester. So we get C double bond O, O6H5, C6H5, C double bond O, OH, and there is a 2H here and then H here. And then this is an ester, OR. And then if we have in water, then we get an acid here. So this is in the presence of C6H5, O C6H5, is an acid. So these are the this is a called dibenzoyl alkene rearrangement. Dibenzoyl alkene rearrangement takes place when a trans dibenzoyl alkene in the presence of light goes to a cis dibenzoyl alkene or Z-ism, and which in the presence of light there is a rearrangement called, and this rearrangement called dibenzoyl alkene rearrangement. Dibenzoyl 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 alkene. So you can see there are two types of rearrangement, two types of interesting photochemistry when there is a proper positioning of the group in the cis orientation, 6 pi electron cyclization of two phenyl group to give a dihydrophenanthrene like this, and then we have two benzoyl groups in cis orientation undergoes a phenyl group migration under photolytic condition to give ketene as intermediate, which in the presence of water gives a corresponding acid, or in the presence of an alcohol gives corresponding ester. Now coming further to look into the 1,4 diene, photochemistry of 1,4 diene. So if you right, this is a 1 2 3 4 5 is a 5 carbon system, 5 carbon system, and this is 1,4 diene. So there is a double bond between one and two carbon, and there are second double bond between carbon number 4 and 5. So this is a 1,4 diene, is a carbon system, and this in the presence of light undergo a very interesting photochemistry is called dipi methane rearrangement. This is a 1 pi bond, is a 1 pi bond, is another pi bond, is a, and then this di 2 pi 1 2 pi means we can call it a dipi methane rearrangement under photolytic conditions. So the product can be visualized on the influencer light. One of the double bond gets excited to give a diradical like this. This is a 1,2 diradical. So stepwise mechanism for this rearrangement can be stated as it is 1,2 diradical, and then there is a attack of this to another double bond to give formation of the cyclopropane. 1, 2, 3, 1, 4 diradical. 1, 4 diradical. The 1, 4 diradical through the formation of cyclopropane, and now this opens up, either this opens up or this double. So this is a newly formed cyclopropane bond. If you open this, we go back to a starting material. So if we open the this old bond, then we end up with a product like this, an intermediate like this. It's a 1, 3 diradical. 1, 3 diradical. And then this diradical can combine to give the vinyl cyclopropane. So vinyl cyclopropane is a very interesting rearrangement. It's called a dipymethane rearrangement. 1 pi bond, another pi bond separated by a methylene group. When we have a system like this, is a simple stepwise mechanism for the dipymethane rearrangement in the presence of light, where the steps can be visualized as the excitation of the one of the double bond to generate 1, 2 diradical, then the attack of one of these double radical to one of the radical to double bond to give a cyclopropyl 1, 4 diradical, which opening of the cyclopropane ring 1, 3 diradical, and then recombination. So vinyl cyclopropane is the product, and this rearrangement has been exploited very well by different group of research people, and then to because this reaction has attracted a lot of attention, because from an open chain system, this is an open chain system, 5 carbon system. Now we are constructing is a cyclopropane ring, 3-membered ring, is a construction of a 3-membered ring which is highly strained, is a very challenging task, and that's for the and also this step where the there is a possibility of either cleavage of this bond, or there is a possibility of cleavage of this bond. So which bond is going to be cleaved is again depends upon the stability of the carbon center radical which is formed after the opening. So this is the reaction is regio selective, because there is a possibility if this bond opens we get one product, if this bond opens we get another product. So out of the formation of two products we end up with only one product which is more stable carbon center radical, and that's why this is a very interesting rearrangement. 1,4-diene undergo dipymethane rearrangement in the presence of light, giving rise to a cyclopropyl derivative product, and the construction of a 3-membered ring strain ring system has attracted a lot of attention, because out of the possibility of two products we get exclusively one product in the major amount, and that's why a lot of examples are available, and a lot of reactions have been studied by different group of people. And so we'll see how the reaction takes place in this in the as I have mentioned, these people have used different say for example, if you have a system like this, so this is a 1 pi bond, another pi bond separated by a methylene group. So this is also nicely set for dipymethane rearrangement under photolytic conditions. So this will, as usual, these these two double bonds are they are not symmetrical. They are unsymmetrical, because this double bond is separated by two phenyl group, and this double bond is there is a presence of a one methyl group, and that's why the as I mentioned, the first step is the generation of excitation one of the double bond, and then the formation of the cyclopropyl radical. So this is the main intermediate which is involved in the two methyl groups. So this is the main intermediate 1,4 diradical through the formation of cyclopropyl group. So this is the main intermediate in the dipyrmethane rearrangement of 1,4-diene. This is a 1,4-diene. Two pi bonds separated by a methylene group. Methylene group, and that's why this is the main criteria for this reaction to take place. Now after the first step on the influence of light, it forms of course a diradical, and then the cyclopropyl you end up with it. Now there is a possibility of formation of two products if this radical forms a double bond here, and if we cleave this is a newly formed bond. If we cleave this, go back to starting material. So this is the old bond. So if we cleave this, say bond A, and then this is bond B. If we cleave this, we end up with a double bond here, and a radical pH and pH here. Now this and then if we cleave this bond B by forming a double bond, cleave this, we end up with methyl group, and this is a radical here, and then this is a phenyl group. Now if these two radicals is 1,3 diradical, if because these two double bonds are unsymmetrical, and then if we combine this, then we end up with a product like this. This is the one product, and then if you combine this, we end a product like this. So this is the first product, and this is the second product. Now out of these two products, only one product is formed, and that is the beauty of this rearrangement. And then and it has been found that here is the selectivity. The most stable radical, you can see this radical is adjacent to the presence of a phenyl group, whereas this radical is adjacent to a methyl group. There is no such stabilization of this radical due to the presence of, whereas this radical is delocalized due to the presence of so this can move inside this, so you can see that this radical is moving all the way to the two phenyl groups and is highly stabilized, and we know that the more stable radical exists and less stable radical here, so this will lead to the formation of double bond and cleavage. So exclusively there will be a cleavage of this bond due to the formation of this double bond. This takes place, and this route doesn't take place, and then this product doesn't form, and then this is the product. Although it is this cyclopropane is in highly strained, you have two methyl groups here and two phenyl groups here, but still this product is formed because of the stability of these this radical which is formed adjacent to the phenyl group, and hence this is a very this rearrangement is very interesting because these two double bonds are unsymmetrical, and separated by two double bonds are separated by methylene group, and they are set for dipymethane rearrangement in the presence of under photolytic condition. And then the intermediate which is formed in the first step is the formation of cyclopropyl ring with a 1,4 diradical, and this 1,4 diradical next step cleavage of the cyclopropane ring, which exclusively takes place in one direction, and the most stable carbon center radical remains and doesn't form double bond, and then this route is more favorable, giving rise to this product as one of the so like this several more examples have been reported by taking an another diene, and then which we will continue by taking few more example and see taking two different alkene derivative.